Okay, so electric potential is the work done per unit charge to move a test positive charge from infinity to a point in the field. And in a radial field like this, we can calculate it using this equation here, where V is the electric potential, which is measured in joules per coulomb, and Q is the charge, and that's in the center, which is measured in coulomb as well. 4 pi epsilon naught, and here 4 pi are constants, and epsilon naught is the permittive of free space, which you can find in your data sheets. And R is the distance from the center of the charge to the point that you're trying to find the electric potential at. Now, if you had a negative charge in the center, then you'd have a negative electric potential, and this equation would give you that negative electric potential. Okay, example number 1, the diagram shows a helium nucleus and an electron. Calculate the energy required to move an electron from 0.50 nanometers to 0.80 nanometers away from the center of the helium nucleus. Okay, so we're moving it from X to Y. The best way to do this is going to be to work out the electric potential at X and the electric potential at Y and figure out the work you must do, the change in potential, to move from X to Y. So let's start off with the equation for electric potential, and we'll apply at X first. Okay, so let's put the numbers in. So charge in the center is a helium nucleus, so that's going to be 2 times 1.6 times around minus 19 coulombs. So that's the Q at the top there. 4 pi epsilon naught, those you can get from your data sheets, times R, so it's currently at 0.50 times 10 to the power minus 9, that's in meters now. And you don't need to square this, so it's just a potential equation. And that gives us an electric potential at X of 5.75 joules per coulomb. Now repeat this whole process again for at Y. Now I'm using 0.80 times 10 to the power minus 9. And that gives me an electric potential of 3.60 joules per coulomb. Now this is quite tedious, so if you try to take a shortcut, maybe you can just do 1 over R1 minus 1 over R2, and then multiply by the constants, which is Q over 4 pi epsilon naught in this case. Do not try to do this where you try to find the difference in the distances and then do 1 over that. That won't work. They're not the same thing. Okay, so now let's work out the difference in electric potential. So to the change in electric potential when you go from X to Y, you're going to have to subtract the distance, the difference in potential there. And that's in joules per coulomb. So we need to multiply by the charge that we're moving, and we're moving an electron, so just times it by the charge of electron that we're moving, which is 1.6 times 10 to the power minus 19. And the change in electric potential energy, which is what we're asked, not the change in electric potential, but the electric potential energy, which is in joules. Okay, so 3.4 times 10 to the power minus 19 joules. Now, is that gaining energy or is it losing energy? So now to move it from X to Y, it's an attractive force. So we'll have to actually push the electron away from the nucleus. So that means we are giving energy to the electron, and its electric potential energy is actually increasing. So it's a positive change in electric potential energy. Okay, example 2. During Rutherford's alpha particle scattering experiment, alpha particles fired directly at the nucleus of a gold atom. And we're given the numbers associated with the gold atom like there. And we've got the mass number at the top, and we've got the proton number at the bottom there, with a kinetic energy of 10 megaelectron volts. So that's the kinetic energy of the alpha particle. That's 10 mega electron volts. Calculate the distance of closest approach R. So what we're doing is we're actually using the distance of close approach, or the closer it gets, to approximate the radius of the nucleus. Okay, so what's going on? So the kinetic energy that it's fired with is turning into electric potential energy because the nucleus is repelling the alpha particle. They're both positive, and the alpha particle comes to a rest. It stops at that point of distance of closest approach. So all that kinetic energy is turning to electric potential energy. So let's turn that kinetic energy into joules first. So start with 10 mega electron volts, times it by 10 to the 6 to 10 to electron volts, get rid of the mega there, and then times by the charge of an electron to turn into joules. Okay, so all that kinetic energy is turning to electric potential energy. So that's the increase in electric potential energy as it approaches there. And that can be determined by using charge times change in potential. So what's the initial potential of the alpha particle? The alpha particle is very far away at the start. So let's say it's at r equals infinity, where potential is defined as 0 and is approaching that point where it stops. And we can find the potential at the point where it stops by using the equation for electric potential, V equals Q over 4 pi epsilon naught capital R. I've subtracted 0 because we're coming from to find the change in potential, but that's not going to have an effect on the equation. It's just subtracting 0 there. So let's put the numbers in. So the change in electric potential energy comes from the kinetic energy, so that's 1.6 times 10 to the power minus 19. And then we've got lowercase q here, which is the charge of the alpha particle, which is 2 times the charge of a proton. There's 2 protons in there. The neutrons don't have a charge. and then the charge of the nucleus of the gold. That's got 79 protons, so it's 79 times the charge of a proton over 4 pi, which is a constant, epsilon is a constant, times r. Okay, so we want to find r. So I'm just going to move the r to the top on the left hand side and bring the 1.6 times 10 to the power of minus 12 down and rearranging like so, put the numbers in, and we get a estimation for the radius of the nucleus, or the distance of close approach, which is approximately 23 centimeters, which sounds about right for a nucleus of an atom. Okay, so what would it look like if I plot electric potential, which is capital V, against the distance from center, which is r? Okay, so if in this case, you can see it's an inversely proportional relationship. And if I plot it, it would look a bit like this, where I haven't drawn the electric potential within the charged sphere here, which is a positively charged sphere. Okay, and it's a reciprocal function, and it should never touch the x-axis like the bottom there. If it was a negatively charged object here, then it would have an electric potential on the negative quadrant, so upside down basically. So in this question, we're asked to show that the electric potential is inversely proportional to the distance from the center. So if we write this proportional like so, we can turn this into equation V equals some constant over R. And if you multiply that V by R, you should get a constant. So let's take at least 3 set of values. So starting off with this one, 3 and 3.6. We multiply it together, you get 10.8. Let's do it again at another point. So 1.8 and 6. Again, you get 10.8. And if we do our third point, again, you get 10.8. This shows that it is inversely proportional because all these numbers are the same as we expect. And if these numbers hadn't been the same, then that would mean that it isn't inversely proportional. So maybe we measured it incorrectly or the theory is wrong. Okay, so another way to do it is actually just looking at the number itself. So if you go from 3 to 6, you're doubling the distance, which should half the electric potential. As you can see, that's what's happened here. And then if you go from 3 to 9, then you're tripling the distance. That should make the electric potential a third. That would be another way of proving that it is inversely proportional. Okay, another way to think about this is we know that the equation here is V equals Q of 4 pi epsilon naught R, and we could just find the constant Q because the charge on the sphere should be a constant. So if I just do 4 pi epsilon naught R times V, you should get the charge. And if I multiply for any set of data, and here I've used 0.06 and 1.8, but you can use any set of data, you should get the same number for them.